Hello everyone. In this video, a quick video, we're going to look at reaction coordinate diagrams. So you've seen these reaction pathway diagrams is what I've called them in the past. This shows reaction coordinates and it actually shows a nice helpful way of seeing how things react, okay? So we got a couple things reacting here. I don't know if there's anything, it doesn't, okay, so we have hydroxide reacting with, it looks like CH3Br, and then you get something funky in the middle here. So notice this is this. This is the funky stuff in the middle, which is right there, which doesn't really exist, but it's somewhere of an intermediate. And then this would be our final, more stable product, okay? This looks like we looked at this and said, oh, this must be an exothermic reaction because the products and the reactants are at different levels. As a matter of fact, the products are lower than the reactants, so it must have given off like this much energy exothermically, okay? So that's how we looked at that. Now, again, some things about this reaction coordinate diagram. So we have this hump here, which I've never really defined as anything. So let's take a look at some of this stuff here, okay? Now, if we take a look at this, the diagram shows the energy of the reactants and products and therefore delta E. As I've already mentioned that the delta E looks like it's exothermic because it's giving more energy. It has released more energy. So I had to put a little bit of energy in. What's up with this energy here, okay? And then to put out this, so there's the start, here's the end, here's my delta E out. It seems to be negative because it's giving off energy. You end up with less than what you started with, okay? At least exothermically. So this middle portion is called the activated complex. In order to get there, you needed to do something called, and add a little bit of energy to make this thing go. So we know that exothermic reactions are downhill processes. Once these reactions go, they go, okay? They go on their own, okay? So going from here to here is a very simple process, but I have this little hill to get over. Requires something called activation energy, okay? So as far as activation energy goes, it's a little bit of a push. This little bit of a push to make the reaction work and have it go is depicted by a capital E with a lowercase a. This activation energy is, again, the energy required to make the reaction work, okay? If I have reactions that are exothermic that require a tremendously large activation energy, yeah, this might be a slow reaction. This reaction right here is probably going to be a very quick reaction because my delta E is so small, okay? So reactions that take tremendous amount of energies and then just go on their own typically are slow reactions. Okay, so this reaction coordinate diagram helps to explain this. All right, so if we take a look at this, in order for a reaction to occur, a minimum amount of energy must first be applied to the reactants. That is the activation energy. Okay, again, another exothermic reaction. It's the minimum amount of energy it needs to break those bonds. So notice that the activation energy is the minimum amount of energy it is to break those bonds and get the reaction moving. Get the reaction moving, okay? So activation energy is, check this out. The answer is here. At what stage of the reaction do atoms have the highest energy? Okay. The answer here is the transition state. It's that activated complex. It is we also call that I'm sorry, not activated, excuse me, the transition state. The activated complex is what you call that, but the transition state is that middle hump, the top of that hump there. What is another name for the activated complex? Okay, transition state, whoops. And the activation energy for this is what? Okay, hopefully you're thinking this answer here. Okay. Potential energy diagram represents a reaction that is what? With the delta H of what? Okay. This one is different. Notice this is the answer here is with the delta H of, looks like it's C. Now, look at how this is different. Now it has, notice I have a tremendous input of energy just to get this guy working. These are endothermic reactions. These are endothermic reactions, and the endothermic reactions require more energy than you get out. So to make this thing work, you have to really plug in that energy, really put in that energy to make that thing work, and that's obvious there. Okay, that's it for this video. Email me with questions.